Well, a warm welcome to anyone joining. Thank you for being here. Go ahead and get yourself ready with a notebook, a pencil, or pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. So I want you to imagine a semicircle just floating in space, flying in space. That's it. No calculus yet, just a nice, calm semicircle. Now, inside this semicircle, you get to put a rectangle. Any width you want, as long as it fits inside of the circle. Any height you want, as long as it fits inside the circle. And the circle here has a radius of 5. But here's the challenge. We want to figure out what is the biggest possible rectangle that we could fit in the circle. So let's take a look at this. Here is our semicircle. That's the best semicircle I can draw. It's actually not too bad. And I've sort of sketched a rectangle in here. I think I should mark this x-axis appropriately. So let's say this is 0, where the center of the circle would be at. This would be our 5, and this would be our -5. So how do we figure out how wide we can make this in order to maximize the area of the rectangle? For example, I could make a rectangle that only goes out to here, and it would be taller. That was not a straight line. It would be taller, but of course, it would be skinnier. So who's to say that that area is better? We're not really sure here. Let's break down what the tasks are for this problem. First, what I want you to do is I want you to be able to represent the area of this rectangle in terms of the width W. Of course, the area of a rectangle is just width times height. But in calculus, especially level 1 calculus, it's going to be important for us to be able to write an equation all in terms of one single variable. So that's what part A has you do. And then for part B, we're going to estimate the width. Just estimating, we're not using calculus yet. You're not there yet. We're going to estimate the width, which will produce the largest area by testing some pretty reasonable values. I'll explain what I mean by reasonable. In fact, maybe I should make this text just a little bit larger, don't you think? Is that better? I think that's a little bit better. Let's squish this like that. Sorry, you guys get a little bit of live edit going. A little behind the scenes there. Okay, those are the two objectives, you might say, along the way in solving this problem. And of course, once you get to calculus, we will solve the exact width that finds this. And you could use a very clever application of trigonometry, in fact, to figure out the exact width, which maximizes the area of this rectangle. Maybe I'll show that at the end, or maybe I'll just leave it as a bonus for you to mention. Okay, so go ahead and give yourself about 5 minutes to do this. It shouldn't take very long. And like I said, a calculator and Desmos is okay to make some estimations. You can make a guess right now what you think the width could be. When you're ready, unpause the video after giving yourself some time to try it for yourself. And you can come back and see how we did it here. Right. So as I started with, the area of this rectangle, of course, is just going to be width times height. Right? Pretty simple. However, we need to express the height as some kind of function of the width. And we're going to use the equation of this circle to our advantage. So the equation of the circle, because it's centered at the origin, would be x squared plus y squared equals 5 squared, or 25. And what you'll notice is that any point on the circle has an x value which is half of the width. So this is our width divided by 2, and this is also our width divided by 2. So the x value in question here is really w over 2 squared plus the y value, which is in fact the exact height. That is our h. So we're just going to call this h squared equals 25. Now we want to find a way to replace the h with w's. And so we're going to have to take this equation and we're going to manipulate it a little bit. So h squared is going to equal 25 minus w over 2 squared, which means h is going to be the square root of 25 minus w squared over 4. Now, of course, whenever we take a square root to solve an equation, we need to consider plus or minus, but we don't have any negative heights here, so we're not going to deal with the negative case. We're just going to presume that it's positive height. And that makes it pretty easy to express our area now, because our area, therefore, is just going to be w times the square root of 25 minus w squared over 4. Now, it would be nice if we could clean this up a little bit, and we can. We have some terms inside of the square root which don't have the same denominator, so we can call this 100 over 4 minus w squared over 4, right? 25 is just 100 over 4. And the reason why we might want to do that is because we can replace the 1 over 4 inside the square root with a 1/2 outside of the square root. You see, I've factored out fourth, and it's still inside the square root, but 1/4 is 1/2 squared. So if I'm showing my work very carefully, this would be w times a half times the square root of 100 minus w squared, which we could also call w over 2 times the square root of 100 minus w squared. Not too bad. This is our value, or our expression in terms of w for the area of the rectangle. So wherever you decide to make the width, whatever your w is, this equation is going to tell us what the area of the rectangle is. We should investigate this because we do have some domain restrictions. I should say domain restriction on w. Of course, w has to be, it should be greater than 0, but it technically doesn't have to be. So we're going to say that w has to be greater than or equals to 0. And what's the maximum width that I could possibly have in order to keep this inside of the semicircle? Well, I have a maximum width of 10 across the bottom. So theoretically, the rectangle could have a width of 10. Now, of course, these endpoints are kind of strange. These are weird, bro. Because those don't really make rectangles. Let me show you that for myself. If I made a rectangle with a width of 10 that went all the way across, in order to quote-unquote fit it in the semicircle, it could not have any height. It would have to have, like, I'm giving it a height just so that you can visually see what's going on, but it basically has 0 height. It has virtually 0 height. Therefore, it has 0 area. So that's definitely not going to give us a maximum area. And similarly, if I make the width 0, it's not even really a rectangle. Again, it's just kind of a little stick, just like it was with the width of 10. It was just a horizontal stick with the width of 10, but now it's just like a vertical stick with the width of 0. So there's really no rectangle to consider the area of in that case. I think it's reasonable to presume that somewhere in the middle, visually you can confirm this, that somewhere in the middle is where the width has to be in order to have any area, and therefore the maximum area occurs somewhere in the middle. It's also a reasonable argument to consider this. If we vary the w, if we vary the width starting from its smallest possible value of 0, in which case we get, again, no rectangle, that's an area of 0. As soon as we start increasing the width a little bit, we start getting some area. And it starts growing. But then as we get to the edge, as we get closer to the maximum width, then our rectangle starts getting smaller and our area starts shrinking back to 0. Okay, so that also confirms that we will get some maximum area in between a width of 0 and a width of 10. This gives us some reasonable values to try to plug in order to see what the area is. And in fact, I've used Desmos. You can use Desmos or any calculator. You can plug in values for yourself. You can plug in whole numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is what I've done here. And I have the equation for the area plugged into this function for the table. You'll notice that as I plug in larger values for W, the area correspondingly increases. It's increasing quite a bit. It looks like it caps very, very close to 25. Yeah, very close to 25 indeed. And then after we pass a width of 7, it appears that our area starts to decrease back towards 0. In fact, it decreases very quickly back to 0. So these would give us a reasonable guess for the width that would produce the largest area. We can say the width is approximately 7. We'll maximize the area. Now, once you get to calculus, you will find a very routine method for calculating maximums or minimums of certain quantities. But I'd like to pose this as a challenge. Is there any way we can guarantee a maximum area without using calculus? That, my friends, is a bonus challenge for you all. I will give you a hint. Trigonometric substitution. And I feel like Hagrid, I've already said too much. Not subscription, substitution. I think I was spelling the word much while I was saying. Not substition. Goodness. I guess that's how you know that I'm not a robot. So I'm messing up on basic spelling here. If you can figure that out, I would be rather impressed if you could figure out how to use trigonometric substitution carefully here in order to guarantee a maximum area. But I'll leave that for you to maybe put in the comments if you'd like. The highlights of this problem include being able to represent a word problem in a situation, extract the equation of a circle, and use this equation, which we would call a constraint equation. Constraint because the rectangle must be inscribed with its base on the diameter and the top corners touching the semicircle. So I'm constrained by the actual circle itself. The corners must hit the circle in order to keep the rectangle completely inside. And we use this constraint in order to represent an equation which involves two variables into only terms of one variable. We replaced the height with the width. We could have also replaced the width with the height using a very similar substitution. And lastly, we used a calculator or Desmos to get us an idea, to get us a feel for what happens as we increase the width on the rectangle. Okay, so when we can see what things are trending towards, then we produce some insights, at least a good starting point. And also, we get a reasonable way to check our solutions at the end when we are doing calculus. We're able to determine that a width of 7 is right around the sweet spot. Technically, it's a little bit closer to 7.071, I think. and that would produce us an exact area of 25. Okay, I think that's enough blab out of me. I'll see you guys next time.